All right, welcome. It is Wednesday, 8/14/2024. Our initial task was to answer the question, how would someone determine their speed? And a good way to do that is to just figure out how far you went and divide that by how long it took you to get there, which I'll write out that equation for us. Speed is distance over time, which is something we talked about already, but it's always good to remind ourselves. We are going to delve a little bit more specifically into speed now, though, and then also get to some other things. But just a quick reminder, in case you're watching this because you missed today. Today was drill day, so if you missed that, you should definitely, the next day you're here, just go around to each of your teachers and say, hey, I missed drill day. Is there anything I need to know? So they can very quickly run you through their class's specific procedures. But for now, I'm going to skip through that and get back into our discussion on speed, which we already said was distance over time. Or if we wanted to use variables, we'd say S is equal to d over t, which is actually a bit of an issue with our notation at least, because the other day we got our first equation for physics, that being the equation for displacement. And we said displacement, let me write this out, displacement was d is equal to xf minus xi. The issue with our notation is that here we're saying that's distance, here we're saying that's displacement. Those are the same variables. That's going to cause a lot of confusion if we don't come up with a fix for it. Thankfully, though, there's already a fix for it. That being, we're going to just add a little vector hat to displacement. That vector hat lets us know that this variable cares about direction. So really with that, I should put vector hats on my position variables as well. Because if you can have positive or negative, then it's a vector. It cares about direction. Distance, on the other hand, does not get one of those little arrows on top because distance doesn't care about the direction. Time, that's kind of a weird one, but for now we'll stick with just saying time doesn't care about a direction, rather it only goes in one direction. Speed, if you look down at your speedometer when you're driving, it'll tell you you're going, hopefully the speed limit, we'll say 45 miles per hour. But it doesn't tell you north, south, east, or west, so it's just telling you your speed. And the units for that, the SI units or the scientific units that we'll all be using, come from really the equation right here. We've already talked about how distance in science is measured in meters, and time in science is measured in seconds. So for speed, the units would be meters per second. All right, so let's run through a quick example on that. So I've mentioned in class that I used to work at the aquarium, and I really think someday I'll probably either go back there to work or more than likely just go there on occasion to volunteer once I'm retired, because it's just a fun place to work. So I did look up and see, all right, how long would it take me to get there? And how far is that? Went on to Google, searched it up, it gave me some numbers, and I did switch them into SI units. Google didn't tell me it would take 3,240 seconds. It told me a certain amount of hours, and I just converted that to seconds. Same thing here. Google knows I'm an American, so it gave me miles, but I just converted that to meters for the sake of our question. But now, let's pretend I'm going to the aquarium after school. Google Maps tells me that it takes that long to drive there, and it's that far. For that to be true, if I'm going to test to see if Google is correct, what average speed do I need to drive at? To do this, I'm going to break it down to a few steps. I'm going to sketch out the problem, list my givens, as in the numerical tidbits it told me, and then identify any missing variables. That's kind of just a weird way of saying, what is the question asking me to find, more or less, which in this case is the speed, and then we'll write down the equation and then solve it out. but I need more room for that, so let me go here. So for my sketch, I really recommend sketches when you're solving physics problems, but keep them simple. They don't need to be pretty works of art. So I'm just going to say S for school, A for aquarium. I'm going from here to here. Should take me 3,240 seconds, and that's 75,000 meters. My givens, I've basically already written them, but just to clarify, distance, 75,000, the time, 3,240 seconds. My missing variable, I'm also going to put under my givens column, my missing variable being speed, I'm just going to put speed is a question mark, because I don't know what it is. Then I think back, or I look at my notes to see, do I have an equation that has all of this stuff? And well, we do now, we just got one. That being speed is distance over time. So then I can just plug into that, divided by the time. And that is certainly not something I can solve in my head, so bring out the handy dandy calculator, and we're probably going to get a decimal number. That being 23.148. So I'm going to round that up to say 23.15. And to get full credit, if I was grading this, I need to put my units, the units for speed being meters per second. There we go. Now, that is the average speed. If we were to look that up, that's kind of slow, to be honest. Since most of the trip is on the highway, one might think I would be going faster than this. But this is the average. This is taking into account the fact that when I leave school, I've got to drive slow. When I get down close to the aquarium, I got to slow down again because you get into that city traffic. It accounts for all of that and just finds the average. When we do it this way, taking the total distance divided by the total time. But now, let's talk about velocity and vectors. Velocity is honestly, I often think about it as the more useful version of speed. Speed tells us how fast we're going. Velocity, on the other hand, tells us how fast we're going and in what direction. Luckily, we already have an equation that we can kind of work from. We already said speed is distance over time. Velocity is very similar. Velocity equals something divided by something. It's still a rate, so it's still going to be divided by time. But instead of doing distance divided by time, we need that thing that has direction, so we'll use displacement divided by time. And that actually clues us in to the fact that since we have an arrow hat on the right side of the equation, we really need one on the left side. And since velocity cares about direction, it gets one too. The units we can also get from the equation itself. The SI unit for displacement is meters, and we already said seconds for time. Now, there's the other word, the other V word up there, a vector. This is a word that you might have heard once or twice in some older math class. A vector is anything with a magnitude and direction. Magnitude meaning it has a numerical component to it, and direction meaning a direction. Either north, south, east, west, left, right, up, down, or oftentimes our direction is just whether it's positive or negative. Only vectors can be negative. Scalars, the other option, scalars just have a magnitude and they're always treated as positive. Distance is a scalar because it's always positive. Speed is also a scalar. It's always positive. Velocity, though, that can be negative because you can travel in the negative direction. Let's look at a couple of those. This is actually one of the more complicated types of questions you'll see regarding velocity, but I thought, let's just throw ourselves into the deep end and figure it out as we go. So what is the average velocity and average speed of a man who runs forward at 4 meters per second for 5 seconds and then runs forward at 2 meters per second for 5 seconds? We'll need to break this down into two pieces. First, we got to figure out how far he went during that first bit where he was going 4 meters per second for 5 seconds. Well, if I wanted to know how far is in like a distance, I could say, here's my speed equation. I want to get distance by itself, so I'll multiply t up. Distance is speed times time, or in this case, that's 4 times 5, which would be 20 meters. And if I really wanted to be fancy with it, I could also use this to find my displacement. Say velocity is displacement divided by time. To get displacement by itself, multiply time up. And we'd get displacement is velocity times time, which is also 4 because it's just forward. We generally treat forward as the positive, so that's still just positive 4 times 5. In this case, it turns out to be the same thing. Many times, your distance and your displacement do end up being the same, but not always, which we'll see an example of that in a moment. That's for the first step. That's how far he went. For the second step, I'll go through this one a little quicker. He ran forward at 2 meters per second for 5 seconds. To figure out how far that is, we just take our 2, multiply by 5, because that's what our equation here tells us to do. 10 meters. Displacement, same thing in this case. Velocity, 2 forward for 5 seconds. Oops. 2 meters per second for 5 seconds. That's 10 meters. So in total, his total distance was 30 meters. That also happens to be his total displacement in this case. So if I wanted to know his average velocity, I would do 30 divided by the total time, which was 5 plus 5, so 10. That's 3 meters per second. And again, for speed, turns out the same in this case. 30 divided by 10, 3 meters per second. And there we go. But these are only going to be the same thing in situations where the person or the object continues traveling in the same direction for the entire time. If there's ever a change in direction, these don't end up being the same. Speaking of, let's say this same person is going to run forward or positive 6 meters per second for 8 seconds. First, how far is that? Displacement is velocity times time. So in this case, that'd be 6 times 8, which is 48. Then he runs negative 4 meters for 12 seconds, which would be negative 4 times 12, which gives us negative 48 meters. So our person here, he ran forward 48 meters, then he turned around and ran the opposite direction, 48 meters. Or in this case, since it's the negative direction, we'll say negative. So in total, his total displacement would be those added together, but 48 plus negative 48 is, of course, 0. That's his total displacement. Which anytime that happens, that's going to make our average velocity 0 divided by, well, it doesn't really matter what, but in this case, 12 plus 8, 20 seconds, 0 meters per second. So it's kind of like he just stood still. Much like displacement, velocity mostly just cares about your starting point and your ending point. Doesn't really care about what happened in between. So as far as velocity is concerned, He started here, and he just kept standing there for 20 seconds, had a velocity of 0. That answers the question, but what if we wanted to know his average speed? Average speed would see this 48, and then it would see this 48, but it wouldn't pay attention to the fact that there was a change in direction. So what's 48 plus 48? 96. So his distance traveled would have been 96 meters, which means his speed would be distance over time, 96 divided by 20, 4.8 meters per second. In this case, they're not the same because there's a change in direction. So if you're having to calculate both speed and velocity, pay close attention, see if there's a change in direction. If there isn't, you'll get the same answers for both. If there is a change in direction, though, of any kind, you'll get different answers. All right, tomorrow we'll be getting some written practice with this, so look forward to that.